Welcome back. This is Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell to get notifications for this series and a bunch of other ones on our channel. Today we're doing multivariable calculus. Chapter 2 is double and triple integrals. We're doing section 2.4, which is applications of double integrals. In particular, I like this physics application specifically, so we're going to do, technically, we already did mass. Moments and centers of mass for planar laminas. Let's do that. Archimedes principle of levers, yeah. That's how you balance stuff. How do you balance a cat with one hand? Archimedes principle, you gotta find the center of mass. So find the center of mass of the cat. What's the center of mass of the cat? I don't know, halfway under your ribcage. She's like, don't ever do that again. This is, which one are you? This is Willa, one of the herd. The herd's about to get bigger. All right, what we're gonna do is first describe, because it was Archimedes and he's a wizard. That's what we do, is wizard stuff. So Archimedes principle of levers. What we want to do is eventually this business, balance a laminar region or find the center of mass of that. What do we mean by that? Let's go back to baby steps and work our way up to what we're doing with applying double integrals to center of mass of a lamina of varying density. So first we're going to start with a rod with two masses, point masses on either end. And we want to find that, so they're possibly different. And where do you find where you're trying to balance the cat? Or this is actually a fairly good example because this is heavier down here and filled with the fluid, and the pen up here is much lighter and there's actually nothing in there. So the center of mass is not halfway between us. It has to be closer to this one. So when it's also round, so balancing that on my finger. Oh, don't use that finger. I'll use whichever finger I want. So you can't, it's hard to do. If it was flatter, I'd be able to do it. But this is the game we're trying to play. We're going to call that the center of mass. So when we draw this diagram, really what we want to do is put it on a coordinate system. Then we arbitrarily mark 0. Then we have an x1 and x2. For convenience, we make them positive. Now we're talking about these two distances. And what Archimedes' principle of lever says, the mass times the distance 1 will have to equal the mass times the distance 2. In one dimension, these are the distance specifically once we have scale on the Cartesian coordinates. Thank you, Renee. Then what I say is this equation, Archimedes' principle of levers, becomes this. Simplifying everything and distributing M1 and M2 and grouping. What am I solving for? I'm solving for the unknown x bar. What is the center of mass? We are given the masses, I'm going to assume. You can calculate the distances between them. And then what you would want is x bar from this. So I'm solving for x bar. There it is. This is what we call center of mass of those 2 points. Now let's scale that up and then talk about how we are going to phrase that business of center of mass for points which have 2 ordered pairs and not just one-dimensional. This is a one-dimensional problem. Let's talk about as many points as we want, masses, and then talk about as many points as we want in a planar region. Then when we do volumes and triple integrals and stuff, we'll do the 3-dimensional version. If we now switched, instead of just 2 particles, if I have a one-dimensional n-particle system, I'm going to call the center of mass x bar, the sum of the moments essentially over the sum of the masses. So these MIXIs are what we call moments of mass, and x bar is the center of mass, and that is viewed as the sum of the moments of mass divided by the sum of the masses, or the ratio of the moments over the mass, the sum of the moments over the sum of the masses. This guy specifically for a one-dimensional system, we only have to talk about one of them, so there's no index, but this is MX technically, and it's called the moment of the system. So the numerator essentially is called the moment of the system. When we do 2 coordinates or 3 coordinates, we're going to have the moment with respect to the x-axis and y-axis, or the moments with respect to the xy plane. Now let's step it up to what if I want, so this is one-dimensional systems. What if I now want to step that up to where I have 2-dimensional lamina, which is what we're going to do, or 3-dimensional object in space, and I want to find the center of mass of those things. It turns out, perceivably, I happen to be in 3 dimensions, so the real game we want to play is when things happen in 3 dimensions. Let's do that. Okay, now what we're going to do quickly is consider a bunch of masses, m point masses, at points in the plane now, x1, y1 to xn, yn. If we have, say, 5 of them in the plane, what we're going to do is look at their x and y coordinates respectively, all of them, and then we're going to sum up the moments and get the total moments. But now we have to talk about not just one moment of the system, we have to talk about the moment about the y-axis and about the x-axis. And at first, especially if you're taking physics class and you actually have to do this a lot, this is just applications in double integrals for us. But it's backwards. You have to remember I'm going about the y-axis, so that's actually talking about all the x's, so that it does match. I don't like the formula. If you keep the sum in there actually and ignore that and write x bar as the sum of mixi's over the mass, then it matches. It's x and x's, but they reference it as the my because it's about the y-axis, unfortunately. I wish they would keep it as the x coordinates, but I didn't make the notation. We might have changed it. Similarly, if we want to look at the moment about the x-axis, we're going to get mx for referencing the x-axis, but that's actually the sum of miyi's, and therefore the center of mass, the y-coordinate of the center of mass of this planar region now is going to be mx over m, which is the sum of miyi's over m, so it does match. Now let's try switching to, this is all, we're assuming also roughly in this scenario that the density doesn't change, but now that we have double integrals, we're actually going to do that and have a varying density over lamina. So let's tie that together. Okay, one last thing. I'm going to talk about the difference between calculating this where I have a laminar region or a planar region where we have constant density versus variable density. There's a few little minutiae going on that I'll try to flesh out, but I'm going to focus on double integrals, and we still haven't even got there. I'm just deriving the intuitive idea of what moments of mass and centers of mass are. Once we have that, what we now want to do is I want to find the center of mass of a laminar region, but we're like, we don't have the machinery the first time we do this in calculus about double integrals, so we say we're just going to make the density constant across the laminar region, and then we don't have to worry about this, and then we can phrase it as one-dimensional integrals, and this is how you do that. For the laminar region, for this scenario, we have to view it as the fundamental theorem of calculus part 1 and 2 and Riemann sums, where we're going to take a positive function f of x and look at the area of the region between a and b. Well, where's a and b? Right, a and b. I go from a to b from the x-axis, y equals f of x to y equals 0. And then that region we're going to say is a laminar region, and the center of mass of that we get specifically from the fundamental theorem of calculus that the area is exactly this integral, and that's how we're going to compute. And the density is mass over area, or if we're looking for mass, that means mass is rho times area, and that's exactly where they get the mass formula from as an integral in one dimension. Then they can derive, I'm not going to do it here, but we'll do a video specifically for the one-dimensional application as well. But this is how you derive the moments about the x and y axis for these guys. Now to derive the x and y coordinate of the center of mass, we do just like we did before. It's the moment my over m and mx over m respectively, and then we put the integrals in, and we notice that it's independent of that constant density. And so we get formulas for, if you have a constant density, you get a formula for calculating the center of mass, which is independent of that density because it's constant. Now what we want to do is start the applications of double integrals and see where do double integrals come in. They come in when we want to start varying the density. What I can now do is phrase this as a double integral and deal with the density being varying over the lamina. Previously we saw that the total mass of a lamina of varying density rho xy was now the mass is, we chop it up and we do the same business. Look at the previous video. And then we get the mass we derived was the double integral over the region D of the density function rho. Now what we do is we have the moments we're going to derive similarly of what I just talked about in the one-dimensional case, but we're going to use the same idea, and we're going to look at the moments about the x-axis and the y-axis. Those end up becoming, don't be confused at first, but we're saying it's the x-axis, so mx actually has the y rho xy, and the moment about the y-axis, my for y-axis actually has x rho x, and then it's going to flip when we do the center of mass. What does that mean the center of mass is? X bar is my over m, and y bar is equal to mx over m. And then if you put that in there, which I'll do in a second, you'll see that the mx, actually the y and the y will match. So I don't like the physics notation. I just like to keep the double integral math notation, and then it matches in my mind. I don't have to worry about this weird indexing match. What? I'm going to write it like this. X bar is equal to my, which I don't like, over m. What if I write it in physics? Then if I write it in math terms, this is the double integral over d of x rho x y dA. And so the x and the x matches, so I like to write this as x bar equals over m. Is the double integral over d of x rho xy dA, and then you can even put 1 over m there. And so I get x bar. And similarly, what I'm going to get is y bar is equal to 1 over m, the double integral of y rho xy dA. And then this is x bar, y bar is the center of mass of that lamina of varying density. Now let's do some problems. All right, example 1, find the center of mass x bar, y bar for the region D, which is bounded by the parabola y equals 9 minus x squared and the x-axis if we have a varying density function of rho xy equals y. What we do is we set up our lamina region as usual. Go look at videos on how to set these up and phrase these as type 1 and type 2 double integrals of general regions in the plane. I have one of those. I see that my x bounds are -3 to 3 and y is going from 0 to 9 minus x squared. Therefore, I can phrase this as the mass, first of all, as the double integral over this region D, and then we have to phrase the moments of mass about that, and then take the ratios to find the x bars. Here we go. The mass, first of all, is equal to the double integral over our region D of just rho xy dA. Now we have our bounds. I can immediately put that as the integral from -3 to 3, the integral from 0 to 9 minus x squared of our density function, which is y dy dx. From this, I'm immediately going to get the integral from -3 to 3 of 1/2 y squared, evaluated from 0 to 9 minus x squared dx. Now we have to open that up. That equals 1/2 the integral from -3 to 3 of, I'm going to get 9 minus x squared squared dx, which I see where they put squared. This is clever. I'm going to get an even function so that I can get rid of this -3 so I don't have to calculate this one more step. Equals 1/2 the integral of -3 to 3 of 81 minus 18x plus squared plus x to the 4 dx. This is an even function. X to the 0, x to the 2, x to the 4, those are all even powers. And so it's going to absorb negative. And what that says is if you have an integral from -a to a of an even function, you can multiply by 2, so I can get rid of this 1/2. What? Equals 2 over 2 integral from 0 to 3 is the move I just did because he's an even function. Check, he's even. What does that mean? Watch our videos on even and odd functions. So I don't have to deal with that guy anymore, is why I did that move. We're going to get enough fractions in here. This is equal to, now, by the fundamental theorem of calculus part 2, the integral of 81x minus 18 over 3x cubed plus 1 over 5 x to the 5 evaluated from 0 to 3. You see why I didn't want to put -3 in here now. At least 0, yay. This is equal to 81 times 3 minus 6 times 27 plus 3 to the 5 over 5, which is 243. -6 times 27. I don't know. If you don't know, you don't need a calculator. It's like, how do I need my calculator? No, you don't. 162. Well, I still want it to be an 8. And then what did I get? Plus this one is some kind of other hot mess. 243 again over 5. It's like, great, now I have to subtract those. How do I subtract those? I don't know. 243 minus 162. That one's easy. I get a 1. Oh, I got to borrow. I'm going to get a 14. I'm going to get 81. Oh, so then now what do I have to do? Erase a bunch of crap or get a bigger whiteboard. Moving that up, I have 243 minus 162 was 81. We just calculated plus 243 over 5. I have to get a common denominator. Every time, it's my favorite dirty trick. One of the two. I multiply by 1 in the form of 5 over 5. Now I've got 81 times 5. If you can't do it, you don't need your calculator. This is 5, and then I get 40, so I get 405. This is now 405 over 5 plus 243 over 5. The denominator is now the same. I can combine the top, which gives me, I don't know how to do that. I've got it right here. So I got 243. I get 8. I get 4. I get 6. So I've got 648 over 5. Now what we have to do is we have the mass. We're going to carry that, and now we're going to find the moments of mass, mx and my, twice. Now what we're going to do is we're going to remember to keep the mass that we just calculated. Then we're going to do the x bar is going to be my over m, and y bar is going to be mx over m. When we calculate these, first let's calculate mx and my. What we're going to do is, what the formula is you multiply by y now. So it's an awfully similar calculation, but we have to multiply by our original function y by y, and then by x in the other calculation is what we're going to do. So you get three integrals that are slightly different, but the bounds are the same, and all of them is what's happening. I don't know if we can do our doubling up trick right now because I don't know if we get an even function, but we'll see and we'll be careful. What do I get? We're going to get mx, therefore, is equal to this guy, which is already equal to -3 to 3 of 1 over 3 y cubed, evaluated from 0 to 9 minus x squared dx. This is equal to the integral from -3 to 3 of 1/3 times 9 minus x squared cubed dx. Now we're going to have to FOIL that out. I have 9 minus x squared cubed, and if you can't remember the binomial theorem or Pascal's triangle and this kind of thing, now from the previous one at least I computed the squared, which was 81 minus 18x squared plus x to the 4. And now I have to FOIL it out one more time, and that's going to give me 729 minus 162x squared plus 9x to the 4 minus 81x squared plus 18x to the 4 minus x to the 6, which is equal to the hot mess that goes there. Yeah, that was the calculation. What do I have to put in there? This guy, if I didn't get it wrong. Moving that up, and after foiling this out, I get this polynomial. Now what I'm going to do is notice that, again, even powers, so I can use the fact that I can get rid of the -3, and we're not going to have to compute those. At least I can use 0 to 3 of this hot mess, and I'm going to divide by the 3. That's going to give me equals 2 times the integral from 0 to 3 of now pushing that through. It's going to give me 243. One last, these are powers of 3, if you remember. And then this is going to give me minus 81x squared plus 9x to the 4 minus 1/3 x to the 6 dx. Now I can finally use the fundamental theorem of calculus part 2 and compute this. This is equal to 2 times, and then I'm going to try and be clever when I do this. So in a second, this is 243x minus 81 over 3x cubed plus 9 over 5x to the 5 minus 1 over 3 times 1 over 7x to the 7, evaluated from 0 to 3. I'm about to put this 3 in here. I'm going to notice that a lot of these powers are powers of 3. Even this 81 is 3 to the 4 over 3, which is 27, which is now 3 to the 3. But let's plug that in there and see what we get. Trying to be clever. Also, I forgot to do it for him. But who is m? M is 3 to the 4 times 8 over 5. But the 8 over 5 also is actually 2 to the 3. So there's the complete prime factorization of this guy. But I'm going to notice when I have to do x bar is my, or y bar is mx over m, I want to know and cancel, hopefully, using clever exponent laws, these types of things. Anyways, I'm getting ahead of myself. Let us compute this. Putting the 3 in there and being clever, I notice that this is 2 times, this is 3 to the 5 times 1 more 3 is going to give me, I'll write it like that if you want, 3 to the 6. And then here, minus 27 is 3 to the 3, and then I get another one, 3 to the 3, or 3 to the 6. Those ones are going to cancel immediately. And then now I'm going to get plus, what is this one? Oh, it's 3 squared over 5 times, and then they're going to give me another one, 3 to the 5. I put that in there. And then minus, now this is 1 over 3 times. Notice I didn't make 21. 21 is useless for me in the calculation. I have 1 over 7, and then 3 to the 7 minus 0. Now what I can see is I can use exponent law to get rid of that guy to help me get a simpler number, and then simplify all these, and I can factor a power of 3 out of the whole expression. Moving that up, I have a 3 to the 6 in both terms. That's going to give me now 2 times 3 to the 6, and then I have 3 over 5 minus 1 over 7. Now, when am I ever going to need to add fractions? Oh, yeah, well, when you're baking or when you're doing the density of a laminar region in the plane of varying density, that's when you need to do it. All the time is when you need to. All the time is the correct answer. 2, 3 to the 6. Now what do I have? I have 3 over 5. The common denominator is, these are both prime numbers, so it's their product, which is 35, their least common multiple. What? Add fractions. This is 7 over 7, my favorite dirty trick, minus 1 over 7, 5 over 5. And so I'm going to get, this is 2 times 3 to the 6 times 21 minus 5 over 35, or 5 times 7, which is 2 times 3 to the 6 times 16, which is 2 to the 4 over 5 times 7, or this is equal to 3 to the 6, 2 to the 5 over 5 times 7. You're like, I wouldn't have wrote it like that. I know you would have wrote some horribly large number over some other horribly large number because you use your calculator. I need to go. No, you don't. That number. Now they're going to simplify if I know what I'm doing. You always do one of these guys over one of these guys, and he's got a 3 to the 4, and he's got a 3 to the 6, and cancel. What does that say? Or now we have to compute my. Luckily, because of symmetry, we have that this guy's a 0, so we don't have to calculate that one. What does that tell us? Now we have to reverse it. Dang physicists. How do we find our center of mass? That's now going to tell me that x bar is equal to who? My over m, which is 0 over m, which is 0. And then the one we have to calculate is using these numbers now. Y bar is equal to mx over m, which is, now we'll use this clever prime factorization and try to simplify. This is going to be mx is this one, 3 to the 6 times 2 to the 5 over 5 times 7. Divided by m is this thing upside down, so I'm going to get 5, 2 to the 3, 3 to the 4. Oh, and then go to my exponent law videos and watch. Oh yeah, look. That's all it is. To make all of these positive, I bring them across and subtract where I need to. So I'm going to bring this one up, and it'll be 6 minus 4. Bring this one up, 5 minus 3. And then the 5's cancel straight up. And I'm going to get 3 squared times 2 squared over 7, which is what? In its common avatar that you would have wrote after you'd use your calculator. 9 times 4 is 36 over 7. What does that tell us? Our center of mass is 0, 36 over 7. Who's 36 over 7? I don't know. 7, list your multiples of 7, 7, 14, 21, 28, 35, 42, meaning of life in the universe, and 49, and da 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 da. Now I have those. 7 goes into 36 how many times? 5 times. And I'm going to get 35, and then I get a 1, I bring it down, goes into 10, how many times? 1, I'm going to get a 7, I'm going to get a 3, it's going to go into 30, how many times? 4, da da da. There'll always be 6 digits, there will never be a 3 and a 1 or a 7, or a 3 and a 6 and a 9, and the decimal, they'll have a 1 and a 4 and a 7 and a 2 and a 5 and an 8 in it somewhere. I'm not going to find it, but if we're throwing horseshoes and hand grenades, I now approximately have that. This gives me what? 5.14. This is 9. Here's, say, 3.5, so 4, 5, there's the center of mass is what it's saying. It's symmetric with respect to the y-axis. It's not with respect to the x-axis, but it's up here in our planar region, and it has more mass and therefore probably density here, but it's telling us it goes up to about 5.1 on the scale from 0 to 9. That's where our approximate center of mass is. Please subscribe right here, hit the notification bell. You get notifications for this series and a bunch of others on our channel.